Welcome to the Explainer. Today, we're taking a classic and, let's be honest, sometimes really intimidating physics concept called Gauss's law, and we're totally reframing it. Think of it as a futuristic cheat code designed to help you completely bypass brutal physics calculations. Seriously, if you've ever felt totally bogged down by pages of endless math, this one is absolutely for you.
Okay, let's jump right in by asking a pretty critical question. Is there a shortcut to calculating complex electric fields without, losing your mind? Because when you look at the standard methods for figuring out the electric field of an object, it honestly often feels like you are doing things the absolute hardest way possible.
And this contrast perfectly illustrates exactly what I'm talking about. Think about Coulomb's law. It's basically brute force integration. You have to take a massive charge distribution, chop it up into tiny little pieces, find the field for every single individual element, and then sum them all up using the kind of labor-intensive calculus that literally haunts physics students' nightmares. But then, you have Gauss's law. This is our elegant, massive time saver. It's a symmetry cheat code that relies entirely on the shape and geometry of the problem, so you can just skip all that heavy number crunching.
So, here is our mission briefing. First, what is electric flux? Second, unlocking Gauss's law. Third, the conductor paradox. Fourth, mastering cylindrical symmetry. Fifth, the power of planar symmetry. And sixth, spherical symmetry revealed.
Starting with level 1, what exactly is electric flux? Let's scan the field lines.
Electric flux, which we represent with the Greek letter phi, is simply the specific amount of electric field that pierces directly through a surface, rather than just skimming along its edge. I want you to imagine flux as this bright neon energy piercing right through a glowing 3D mesh. We don't care at all about the energy flowing parallel to the mesh. We only care about the exact amount of the electric field that is actively penetrating that surface.
So, the most crucial point here is captured in this really simple rule. An inward piercing field gives you negative flux, an outward piercing field gives you positive flux, and a skimming field, one that just runs right along the surface without actually going through it, is an absolute zero. If you understand how to just look at a surface and tally up what's coming in versus what's going out, well, you've pretty much mastered flux.
All right, moving to level 2, unlocking Gauss's law, the core algorithm.
Now, what's incredible here is how this algorithm links that neon flux we were just visualizing directly to the net charge trapped inside. The equation is epsilon naught times phi equals Q enclosed. But in everyday terms, it just means the net flux popping through a completely closed imaginary surface, which we call a Gaussian surface, is directly proportional to the net charge enclosed within it.
This gives us a brilliant inside-the-box analogy. Think of it kind of like knowing exactly what's inside a wrapped birthday present purely by measuring the light piercing outward through the wrapping paper. You just cast a holographic closed Gaussian surface around your object. Then you measure the outward or inward piercing field lines. And from that alone, you can calculate the exact charge inside without ever having to open the shape. From this incredibly simple framework, you can actually turn around and effortlessly derive Coulomb's law.
Now for level 3, the conductor paradox. What exactly goes on inside the metal? Let's watch this electrostatic equilibrium sequence play out. Picture a solid lump of copper. Step 1, we add excess charge to this isolated conductor. Step 2, because like charges repel, the internal electric field immediately starts pushing these mobile charges away from each other. Step 3, those charges flee and hit the absolute outer surface, spreading out as far away from each other as they physically can. Which leads to Step 4, the internal electric field drops entirely to zero. The excess charge lives exclusively on the surface. If you try to use Gauss's law inside the metal, you find zero flux and therefore zero enclosed charge. It is complete electrical silence on the inside.
Let's step it up to level 4, mastering cylindrical symmetry with infinite lines of charge. If you have a wildly long uniform line of charge, trying to use Coulomb's law to find the field is a total nightmare. But by simply wrapping an imaginary Gaussian cylinder right around that line, the electric field calculation suddenly becomes incredibly simple. The field lines pierce only the curved part of the cylinder. They just skim the flat end caps, so the flux there is exactly zero. That means this incredibly complex math collapses into a beautifully simple equation. The electric field E simply equals lambda over 2 pi epsilon naught r. By just matching our imaginary 3D shape to the shape of the line, we completely hack the math.
Level 5, the power of planar symmetry for infinite sheets and plates.
The crucial trick here is how we slice right through the plane.
Whether we are dealing with an infinite non-conducting sheet, like a giant piece of charged plastic, or a conducting metal plate, we just cast a cylindrical Gaussian surface straight through it. For the non-conducting sheet, the field points perpendicularly away from both sides, which gives us a magically uniform field of sigma over 2 epsilon naught. But for conducting plates, well, as we learned in our paradox level, all that excess charge leaps to the outer faces. The internal field is 0, which actually creates a stronger uniform field on the outside equal to sigma over epsilon naught. And the craziest part? It is perfectly constant. It doesn't drop off no matter how far away you move.
Finally, Level 6, Spherical Symmetry Revealed.
Think about different uniform distributions of spherical charge. Because a sphere has absolutely perfect symmetry, our imaginary Gaussian sphere captures the outward piercing field completely evenly across its surface. And what this proves is something super powerful. A uniform ball of charge acts exactly like a single, tiny point particle as long as you're looking at it from the outside.
Now picture a hollow spherical shell where all the charge is concentrated solely on that outer boundary. If you were to put a Gaussian surface inside that empty shell, there is no enclosed charge at all, meaning the net electric field inside is absolutely 0. It mathematically masks anything inside, protecting the interior with a net 0 field. It's essentially the ultimate electric shield.
All right, here are the ultimate cheat codes we've just unlocked, allowing you to completely bypass terrifying calculus using nothing but pure geometry. For cylindrical symmetry, the field decreases as 1 over r. For planar symmetry, the field is magically uniform and constant. It never fades. For spherical symmetry, the field decreases as 1 over r squared on the outside and is exactly 0 inside hollow shells. And finally, for conductors, there is always 0 field inside, and the charge lives entirely on the outer edge.
To wrap things up, I want to leave you with a pretty provocative thought to ponder. If we can use this symmetry trick to hack electric fields so perfectly, how might it apply to other fundamental forces in our universe? Could there be a Gauss's law for the pull of gravity? Keep questioning, keep looking for those elegant shortcuts in the universe, and thanks for joining me for this explainer.